We often use the language of waves when we talk about light, and so it's helpful to just talk a little bit about some of these terms that we'll be using throughout the course as we talk about light. So here's just a generic wave simulator, all right? And it's like a string, and there's this little oscillator going back and down that causes it to create waves. And these waves travel on the string. So this is just like if you took a slinky and were just waving your arm back and forth, you'd get waves kind of like this as well. These are sort of perfect waves because I've removed any friction or anything like that. Now, one of the things we talk about as we talk about a wave is the frequency of the wave. The frequency of the wave is how many waves are going by every second. So if I look at the door and I were to take a stopwatch to measure 1 second, I'd probably see, oh look at that, I can find a timer right here. I'd measure 1 second and I'd count how many waves go by. One wave. It's like 1.5 waves went by in a second. Alright, so the frequency would be like 1.5 waves per second. Now, that's one way to talk about it. And when we talk about light, we often find it more useful to talk about wavelength. And wavelength is related to frequency very, very closely, but wavelength is the physical distance from one peak to the next peak. So if I pause this, I could measure from this peak across to this peak, and that would be the wavelength. I can even put this ruler on here and measure it. It'd be about 40 centimeters in this case. Now you can see that wavelength and frequency are related because if I were to turn this frequency way down, alright, you see that the number of waves passing each second has decreased. There's one wave, it's like less than a wave in a second. And you'll also notice that the distance from one peak to the next peak is also much longer. Right? So when we have a lower frequency, we have a longer wavelength. They're connected that way. And likewise, if I turn up the frequency to make this thing go really fast, and I have lots of waves passing every second, doop, 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 doop. If I pause it, the distance from one wave to the next, the wavelength, is much shorter. So we can talk about a wave in either way. Now, when we talk about light, we often talk about how the wavelengths of light change dramatically. Right? From like radio has very long wavelengths, and infrared, or I'm sorry, all the way up to X-ray has very, very short wavelengths. One other thing we can see, and I'm just going to mention this just in passing, is that energy, the idea of energy, is also related to this. So you can kind of get the sense that if I have a really high frequency, there's a lot of energy in this motion, up and down and up and down and up and down and up and down. Whereas if I go to really long wavelengths, it looks a little like there's a lot less energy here. And that's true. I mean, radio waves carry a lot less energy than, say, X-rays, which is why radio waves aren't very dangerous to us, whereas X-rays are quite dangerous. So just that idea that energy is also playing a factor in here, but that it's really related to wavelength and frequency. So when we talk about a light wave, we can talk about it interchangeably, talk about its frequency, its wavelength, or its energy. We're really talking about the exact same thing. We'll more often than not talk about the wavelength. But I also want to say that there's one more complicating factor, and that's color. And we'll talk about that more in the next lesson. So let's just look at this whole range of the electromagnetic spectrum. So we have here all the different parts: radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. And you can kind of see here how it's visualized with these wavelengths here, right, where these are much shorter wavelengths. Now, to give you a sense of the size of these wavelengths, right, this covers such an enormous range. I mean, we simplify the whole spectrum of light down a little too simply sometimes, I think, because this is a huge range. Radio waves can have lengths of thousands of meters. So like a half mile or more, a whole mile, could be the wavelength of a radio wave. So the size of a radio wave, these oscillations, which are kind of these weird oscillations of electricity and magnetism, could be as big as a whole building or maybe a person. We get to microwaves, they're not that small, the size of small insects. And infrared, the actual waves themselves, are maybe the size of a pinpoint. We get down, though, ultraviolet and X-rays, those oscillations are so small they're the size of individual atoms or just atomic nuclei. So incredibly small, the smallest things imaginable. And the frequency here you can see as well, it's increasing, right, as we go across. Now, one other way we sometimes talk about wavelength is as color. We would say that the wavelength of red light, okay, is over here, but as you get shorter wavelengths, if we look at just the visible part of the spectrum, you get shorter wavelengths, and that becomes blue light. So we can kind of talk about, so like for example, red light has a wavelength of about 600 nanometers, or 600 billionths of a meter. Blue light is about 400 nanometers, right? So the color actually corresponds. What we perceive as color, what we're actually measuring, what our eyes are really measuring, is the wavelength of light, which is quite amazing. All right, so those are kind of connected to each other. In the next lesson, we'll see how temperature connects to all of this. Now, one way I just want to illustrate again how enormous this range of spectrum is that we could just say, oh, it's the radio waves and it's just a small part of the spectrum. But I want to illustrate for you just the radio waves, how huge that really is. So this is a map, right, of the full radio spectrum and how it's broken up into different kinds of uses. Right? I mean, you think radio is used by a lot of different things. Like radios obviously use radio waves, but also televisions. When they broadcast over the air, they use radio waves. Airplanes, when they communicate, they use radio waves. When our cell phones communicate, they use kind of radio waves. So this whole spectrum of light has to be broken up for different people to use it. There's a lot of companies that depend on radio spectrum, and if this wasn't broken up, then we'd all be interfering with each other. Your GPS signal would interfere with your cell phone signal, which would interfere with, emergency like search and rescue signals. So this is all broken up in the U.S. For our spectrum here, like the radio waves that are going across our country, but it's also done internationally. Let me just zoom in so you can see what a couple of these things are. It's kind of interesting to see. So I'm going to zoom into the spectrum, and you can kind of see the stuff that's breaking up our spectrum. So you can see like aeronautical mobile. So this is like airplane to airplane communication, right? Here's amateur radio, so they can communicate amateurs. Land mobile, that's like cell phones. Right? Maritime mobile, that's just for boat communication. Radio astronomy, there's this narrow little range, and it's hardly any of the spectrum as you look at the whole thing, but this is reserved just for astronomers who want to study space in a very specific wavelength of light. All right, so you see this kind of cool stuff. Let me go to one other part here. You can see like this is television. This whole section is television signals. Here's more television signals broadcast. And then down here we can see how crowded it gets, right? Mobile phones, Earth exploration satellites, radio location. It's crazy. All right, so there's a ton to these spectrums. We're just looking at the highest level and how we can kind of break it into these broad categories. All right, so very cool. We can see how the language of waves applies to light in particular, and really how big this whole spectrum really is.